Okay, let's go from that. It should be 2016. All right. Okay, so these slides are fairly well consistent. I don't change them over the semesters because we have a fairly stable sort of content. Okay, welcome everyone to Computer Games and AI, or AI for Games. This is our first lecture. In this lecture, what I will do is I will go through and introduce myself. I am Dr. Rune Rasmussen. You can find me in Y Block on level 6. Now, of course, you won't have access to that level, but if you go to level 5 and you wanted to contact me that way, you could ask so if we had a meeting, you could go to level 5 and there's staff there and they could send through a message to me. You can send me an email via my email address. I've got my phone number there, so if you need to contact me, there are a number of ways that you can contact me. Usually telephone number in level 5 would be if we've already arranged a meeting, a consultation meeting. If you want a consultation meeting with me, first email me via my email address. When you send an email, I guess you've probably heard this sort of statement made in many units before mine. Use proper English language, don't use text language. Give me your student number so I know who you are. So often students will send me an email, they want consultation, they might give me some kind of handle that they use and it's not their real name, and then I can't find out who that student is or what their history might be in terms of how they've been performing and so on. So information like that is often useful when having consultation. In addition to that, I've also got a tutor who will be taking care of our workshops. His name is Harrison Shell. I haven't put his name up on here, but I'll introduce him next week when we do the workshops. So just so that you know, there are no workshops today. Workshops begin in week 2. Okay, so what I'll do is I'll run through first an introduction about the unit, and then I'll about the administration side of the unit. And then what I'll do is I'll give a brief introduction into Game AI and what it means for us moving forward over the next couple of weeks. Now, to succeed in this unit, attend the lectures. A lot of students, I've had students in the past who I never saw and would come to me in the final weeks wondering how they're performing and not really knowing any of the content. So attending the lectures is very important. Attend the workshops. So in this unit, and this is really important, in this unit the workshops are really important. They contain a lot of information about how the methodology and how artificial intelligence methodology for computer games is actually applied in a games engine. So attending the workshops gives you that tactile, hands-on experience. It sort of gets your cognition going about the whole thing. You're able to see what it does in software. You're able to experience what different search algorithms and different approaches perform like under different conditions and so on. So attending the workshops is really important. It's also a great way to concrete some of these ideas. So definitely do the workshops. Do the workshop exercises. So there are a few weeks where if you've looked on Blackboard, where I don't have workshops, and these are usually the weeks where we're doing assignment work. Otherwise, all of the other weeks have workshops, and doing those workshops is really critical for your success. Complete and submit the assignments. I think this is a fairly obvious one, but again, I have students who do not complete or submit assignments on the occasion and will ask me, why they're not performing well, or will ask me, or will come to see me about how they might still perform well even though they haven't submitted assignment work. So the answer is submit the assignment work and submit the assignment work on time. So now we have these deadlines which came in a couple of years back. If they're not submitted on time, then admin want to give you 0 for it. Generally, my policy is if you're submitting and you're submitting online, and let's say the cut-off time is, say, 11:59 at night, and you submit it, say, 2 minutes late, I'm not going to deduct or worry about that sort of problem. This whole rule about 0 marks doesn't come from me. This comes from QUT administration. So my tendency is to try to be as fair and as lenient as possible. But of course, if students are going to submit assignments that are, say, a day or 2 days late, then I will, I'm actually forced to comply with the policy of QUT. Do just as what is required. Now, this is really important because we're dealing with a topic that has a lot of visual content. So we're dealing with artificial intelligence in the context of a games engine. And you have all this ability to put all kinds of really flash, characters, objects, and all kinds of imagery and all kinds of work into that game engine. That kind of stuff's not really important. What's really important in AI is the methodology itself, the implementation of that methodology, and understanding what the methods do. So often in the assignment work, there is a criteria sheet. It's fairly precisely specified. Just do what's required. Don't have to go overboard and do extra. There is the last assignment. I do have a mark in that last assignment for visual content or appeal, but it's a very small mark and shouldn't be considered a large part of that assignment. Eat well, sleep well, exercise. I think this is the general banter that you hear from many unit coordinators. Okay, so in artificial intelligence, pre and post conditions are really important, and we'll get onto that when we start doing planning algorithms. So wanting to have success are pre and post conditions of your choose to succeed function, right? So you should think of yourself having a choose to succeed function and success being the pre and post conditions for it. Wanting success being the precondition and having success being the post condition. Okay, so there will be 5 key objectives in extracting information from the lectures. The way I structure the lectures, I do it in several layers. Because of the content that we're delivering here, having a very strong mathematical bias to it, I deliver it in 3 ways. I deliver the mathematical aspect of it in pure mathematical notation. I deliver algorithms and pseudocode, and I also deliver it with high-level conceptual diagrams and conceptualization of the idea itself. So what we'll generally do is I'll show you the mathematical aspect of it, then I'll show you algorithms, and then we'll step through those algorithms in diagrams and so forth. Okay, so key objectives: identify and explain different types of AI agents. So throughout the weeks, I'll be talking about different classes or different categories of artificial agents and how they differ from one another and what features they have that make them different. Recognise and write algorithms using a pseudocode convention. All right, so I do have a convention document on Blackboard, which I'll show you. That should come under additional materials. There's additional material here. Some of it's not really useful. OpenSim, for example, is not useful for this unit. And by the way, you won't be able to see that, so I'll put it on student view. So this is what you'll be able to see. There's a pseudocode convention document that I've got here. It's just a general specification for pseudocode, and by the way, that was the code many years ago when I first delivered this unit. So it's just a general specification for pseudocode. It's a good resource just to have a quick look and understand what different parts of pseudocode mean or imply. But if you follow this in a fairly, you don't have to follow it exactly, but if you follow it, in a fairly good way, I'll be able to understand your pseudocode, and we'll be able to, when you deliver that in your assignments, we'll be able to be on sure ground that we can understand. I can understand what you've written, and you can understand any comments that I give back. Identify and explain the different structures and automations used to represent and solve problems. So it'll be important for assessment through this unit to be able to look at different structures. So we'll look at different kinds of search structures. For example, we might be looking at some search structures which are just what I call graphs, and I'll talk more about those over the next couple of weeks. And other ones that might be directed graphs. Then we might have other search structures that might be trees, but they're actually kind of implied trees. We don't actually have them explicitly, and so on. So there's different kinds of structures that we'll be looking at, and then we'll be looking at different kinds of automation around those structures in order to facilitate something that looks like intelligence in our agents. Explain the usage of different algorithms, structures and automations in the context of various game applications. So sometimes one of the big problems with computer games is that there's limited resources for artificial intelligence. So at the tail end of any kind of game development, there's a little bit of resourcing available for such things as artificial intelligence. It's becoming a bigger slice of the pie because more resources are made available, and games are reaching that point where they don't need to be using up all the resources on a machine all the time. So that kind of constrains what kind of algorithms we can actually use in a video game. And some algorithms are better than others. Some perform better under different conditions, and we'll talk more about those over the next couple of weeks. But being able to identify the situation where a certain algorithm is better than another algorithm, it will be definitely something that we'll be covering over the next couple of weeks. Also use the prescribed terminology. So throughout the slides, I actually highlight terminology. So when it comes to assessment work and assignment work, that'll be one thing that I'll be looking for. Do the students actually use this terminology and understand what the terminology means in their assessment presentations? All right, as stated before, workshops will start in week 2. Of course, I think everyone allocates even before week 1, but allocate to exactly one workshop and attend that workshop each week. This is no longer a great big thing. We've had Alienware and Fishbowl for ages now. I keep, every year I look at that and I think, why didn't I just delete that already? But it's there. So we'll be in the game lab over in S Block. In fact, this year, this semester we'll still be using the existing machines there. Unfortunately, we don't get the new machines until next semester, so that's a bit of a shame. The butterfly rule for this unit. A simple object that represents a butterfly is as good as a fully articulated animated butterfly. So this kind of harks back to this whole thing that I don't need in the assessment work all kinds of beautiful rendered objects. I just need objects that have scripts associated with them, and the scripts are beautiful and do all kinds of wonderful things because of their great algorithms. All right, in our programming environment, so we'll be using Unity 3D as our game engine. Sometimes students might think that we should use UDK or Unreal. These are also very good engines. Unity 3D is one that we've selected because we have a license for it and so forth. We used to use something called Open Simulator. Now, Open Simulator was a Second Life, open source version of Second Life. It was useful in many aspects because it was very easy to prototype in that environment. But on the other hand, it was very clunky. It didn't have very good graphics. Sometimes the scripts kind of ran very slowly because they were interpreted within an environment which was interpreting an interpreted language. So go figure that one. Some years back, this received very poor feedback from my students. Open Simulator was useful also because we're using it in other research at QUT, and it kind of had that synergy, but we don't do this anymore. So if you've ever heard any bad rumours about this unit and Open Simulator, we don't do Open Simulator anymore. Everything will be in Unity 3D. Okay, as you already know, most of you probably played around with Unity 3D. It's a commercial game engine, but it does provide a free community license that you can install on your personal computer. We'll be using the latest version. That also means that I need to go through my workshops and make sure that my workshops will run in the latest version. How many people here are not familiar with Unity 3D who haven't used it? So okay, so we've got a few. The first workshop that we'll do next week is a fairly basic workshop, and that will be an induction workshop that gets everybody up to speed with Unity 3D. So for those who are familiar with it, you'll have to be patient in that first workshop, and for those who are not, this workshop will get you up to speed. Unity 3D provides scripting in both JavaScript and C#. And then there's another language called Boo. I've never used it. We'll be sticking with C#, mainly because other programming units within the various degrees, for example, IT23 and software tech in the games degree, have a unit that teaches C#. So you should all be familiar with C#. JavaScript is also a nice language. How many people here are more familiar with JavaScript than C#? How many people here are not familiar with C#? All right, so we're good. Good. Okay. Okay, this is another thing. Scenes that you build and generate in Unity 3D can be executed in Unity or built and saved as an executable. So this might be important. This is kind of important when submitting assignment work. It's really handy. It's really handy when students submit both their full project and an executable, because if, for example, there's a mismatch between Unity 3D on somebody's computer, say a Mac, and I'm on a Windows machine or something like that, and there's some sort of file mismatch, if I can see an executable and can run it, that's awesome. So I've had this situation in the past where I'm not sure what the difference was between the student's computer and mine, but there was something corrupted in the project file, so I couldn't open it, but they had an executable, and that just made marking the assignment, so much easier. All right, we'll rely on some degree on tutorials available in Unity 3D. So there are these tutorials, and they're very, very, very good. I'll open up their website so you can have a look. And I encourage you to actually spend time on the Unity 3D website and looking at their tutorials. All right, so there's different topics, scripting, for example. You can look at that one. There's a whole bunch of scripting tutorial examples up there that are worth looking at. So getting familiar with Unity 3D and taking a look at these tutorials would be a very good advantage. Would put you in an advantageous position earlier on if you do that. Yep, okay, so there's plenty of stuff here. Scripting as behaviour components, if statements, loops, look at, all sorts of things, dealing with cameras and characters and objects and so on. Right. So before next week, to get everyone up to speed, I recommend you get a version of Unity 3D on your personal computer, and then also spend some time reading the user manual, just so that you're familiar with the Unity 3D environment and the different contexts, the different control panels that are in Unity 3D and what they actually do. And also do some simple tutorials as you follow that manual through. So I actually found Unity 3D and its manual very good in inducting the reader into their system and getting used to actually using it. Oh yeah, okay. So we've made use of Unity 3D. We did that in 2014. That's just historical. This is also true, even though this harkens back to 2014, I'm still updating slides and material in the slides, not because they are, the information is legacy, but because Unity 3D is changing all the time as well. So I think last year we had version 5, this year is, I don't know what the version is now, but I suspect, again, I'm going to have to make some updates to the slides in order to make sure what I'm showing is consistent with the software that you're using in the labs. Okay, so about assessment items. We have 2 assessment items. We have a minor assignment that's worth 20% and a major one that's worth 30%. I used to have postgrad students as well, and when I had postgrad students, they would do something different from the undergrad students. This is no longer the case, which is good. I can talk now to a cohort of students and not have to switch and cut between whose content is what in the same room. So everyone will be doing the same stuff. In the minor assignment, we'll be looking at state machine artificial intelligence, or AI based upon state machines, and also pathfinding in a space lab environment. And then for the second assignment, we'll be looking at swarming. So what swarming is this idea that you have these agents that can compute some sort of local information, but together all of these agents make a global phenomena like bees flying around, or birds, or fish swimming around in a fish tank, and so on. Workshop exercises will assist in building the base code for each assignment. So this is what you'll find as a part of the learning experience, is that as you go through the workshops, you'll see that components for the assignment are actually being implemented as a part of the workshop. So when you get to doing the assignment, you can actually refer back to the workshops and take pieces of code and pieces of learning that you had from those workshops and actually integrate it into the assignment. Then there's a final exam. I'm inclined to try to do this final exam school-based and do it as a quiz on Blackboard, rather than sitting 2 hours in under exam conditions. How do you guys feel about that? Pretty good? All right. So I'll do that again this year. I think it's much more conducive because you have more time. You're not stressing out about an assignment at the end of the semester. An exam at the end of the semester. And it's something that I can set up and get running during the semester so that you actually have time to answer those questions. Okay, so I talked about this already and I've showed you the document. Lecture slide, workshops and assessment items will be using a formal pseudocode convention to describe various algorithms. So it's got a description there of where that link is on Blackboard and where you'll find the document. You'll be required to use pseudocode convention in your assignments. So, like I said, if you're close to that convention and it's easy to understand what you've done, we have a good means by which to communicate our ideas with each other. All right, weekly outline. Now, there's some things to note here. This week 12, I'm going to point out straight up, is probably not going to be taught. we actually have a number of Mondays which are public holidays over this semester. There are actually 2 Mondays that are public holidays. So it'll mean that week 12, which was really a fill-in lecture anyway, it was more like a, all right, this is what's interesting out there kind of lecture. It doesn't really actually provide any information towards your assessment or anything like that. It's really just a tail-out lecture. So what that means is that as I space these weeks out over the next 13 weeks, there'll be 2 weeks which are public holidays and there'll be no lectures on those 2 weeks. But this is the general order. This is the order in which the lectures are delivered. There's this week that gives us the unit introduction. Next week we'll look at navigation structures and basic graph theory, and then we'll look at algorithms for pathfinding. Week after that we'll get right into pathfinding. Now the reason why I put a lot of focus on pathfinding is because the search algorithms used for pathfinding is very conducive and very comparable to many other kinds of algorithms used in artificial intelligence. Artificial intelligence is very strongly based around this idea of searching. So you search a large space, you end up with some kind of solution, and that solution kind of represents, when it's implemented in an agent, some sort of intelligence. So as you've seen with pathfinding, you do a search of a space and your agent is able to follow a path, and it looks like the agent has thought about how to get around objects. It's the same for other things, like you might want an agent to be able to come into a room, move some tables and chairs around, open a door, and walk out through another door, and the entire configuration of that space has changed, as though the agent had thought about the space and had set it up for something. So it's this kind of effect that we try to create with our agents, and so all of this requires some searching. An agent would have to search through the space of objects using a certain language on top of those objects, and come up with a solution on how to rearrange a room, for example, in order to arrive at some optimal condition. So searching is very, very important in AI, and that's why I put such a focus on it in the first 2-3 weeks. In week 4, we'll start to look at AI agents as a concept, and we'll look at the different components of agents and what they mean. Then we'll look at finite state automator, which is really the most basic kind of agent. And as we go along in the weeks, we build up different kinds of agents. So we start off with something really simple like a state machine agent. Then we look at an extension on state machines called behaviour trees, and different kinds of effects that they can, or different kinds of expressions of language that they can permit, which makes the agent more intelligent. Then we'll look at what's called logic agent and knowledge-based agents. These are agents that are able to actually store information somewhere in a database and retrieve that information in order to make decisions. Then we have planning agents. These are agents that are able to search a space and come up with a plan to arrive at a goal state. We look at probabilistic methods. This begins to push the boundary of or make the agent do things that would be seemingly intelligent just because there is some sort of statistical component to it. The agent is no longer purely predictable. There is there's some uncertainty about what the agent might do, but yet in that uncertainty the agent always seems to do something sensible. Then we look at swarming intelligence, which is, again, it's actually a kind of extension on probabilistic methods, because we're dealing with multiple agents at once, and all of those agents are being managed by a very simple kind of collective program. We'll look at board game AI. Board game AI extends this problem from the agent itself just doing something based upon a static environment to agents doing things because another agent is also doing something else. So with board games, you have this problem with one agent is trying to make moves to win, and the other agent is trying to make moves to beat that agent or to prevent that agent from winning. And so each agent is interacting in such a way that their effect on the other agent has to be considered in their contingency. So for board games, agents have to really search all of the possible things that the other agent might do, which is different from searching a static environment. And then we would have had week 12, which would have been the phase-out week, where I would have just shown, looked at something that might have been interesting in terms of, what's on the horizon, what new kinds of methods or techniques are out there, and that would have been a week where we would just sort of conclude the 12 weeks of the unit. Okay, so how are we doing for time? Alrighty. Generally what I do, so I'd be starting the lecture for week 1 now. Generally what I do is I have like a 5-minute break, but I think this lecture generally runs short. So what I'll do is I'll present this first week material, and then at 11 o'clock I'll give you a 5-10 minute break, and then we'll finish it in the last half hour after that. Is there any questions that you guys had before I begin this? Yes?
So do we have no lectures or workshops in week 13?
What's going to happen is we have those public holidays, so we'll actually have a lecture and work. Well, probably not probably not a workshop in week 13, but there will be a lecture. No, actually, there will be a workshop. There will actually be a workshop. So we have the board game AI, and then there will be a workshop for board game AI as well, because I've got an artificial player for that workshop. So that'll end up being in week 13. I'll renumber these so that it makes better sense. As you can see, because we have the 2 public holidays, that adds 2 weeks to the end week, and that'll be in week 13. Any other questions? Good? Okay. Alrighty, so what is game AI? What is it that we're trying to do here, and where did it all start? It's often, when you look at your characters in a game and they're able to do sensible things, you wonder really what is involved in making that agent do what it does. It may actually seem very clever and intelligent of what this agent is doing, and you might think that this is something very complex or something very deep and intriguing, and so I guess this is what attracts a lot of students to this topic. But in fact, AI has this history, and if we look at the history of AI, we begin to look at what the gradual developments were to our current state of art. So if we look back in the 1970s, movement for non-player characters, NPCs, were all pretty much hard-coded. That is, that they would write some software, and it would involve if-then-else statements and loops and whatever. But basically, your agents would just simply follow this code, and it was completely scripted. Your agents wouldn't do anything outside of it. So if you think about, video games like Pong. I've got Space Invaders up there as well. And the Space Invaders video game pretty much just involved a set of aliens that were just moving as a block across the screen backwards and forwards and getting quicker and quicker. And then you had your player, which was a little spaceship that was running down the bottom and trying to shoot around some blocks. And those blocks provided protection from any artillery coming from the aliens. But at the same time, if you shot through the blocks, you were exposing yourself. And you had to kill these aliens off before they got to the bottom. So all of the AI for your non-player characters, which were the aliens, was simply a code that caused the aliens to move backwards and forwards like this and get closer and closer and faster as it came to the bottom of the screen. Simple as that. So that was the state of AI in the 1970s. Just something scripted up in code. In the 80s, unique movement patterns of different NPCs and the use of some uncertainty by random pattern selection. So, for example, Pac-Man. If you remember Pac-Man, you had the ghost would fly around, the different pathways, and your Pac-Man had to go through and eat all the whatever it was, space junk, in order, and also get away from these ghosts at the same time. But the movements of these characters, while they were still somewhat scripted, could sometimes make random choices and go in different directions in that space. In the 1980s, again, finite state machines, very much, so if you think about scripting is good, but it becomes hard-coded in the software, or it becomes hard-coded in the program itself. What's better, though, is if we have a way of reconfiguring our agents. And when we look at script really just creates a state machine agent in a way. It's really just an agent that changes state through some if-then else statements and acts upon those states. But in the late 1980s, the whole idea of having finite state machines that could be expressed as some data that gets uploaded by your game engine, and then your agent simply responds to that state machine, became in the fore. And so you would find in a lot of games from that point forward there'd be these files that would define the finite state machines for your agents. And these files would actually be created by your level design tools. So things like EA Games had various sport games like soccer and football, Dune 2, for example. So you had these characters that were still finite state machine based, but you could upgrade the game with different kinds of mods. All right, in the 1990s we had video games that looked at much more interesting methods, things like constraint satisfaction. So in constraint satisfaction we might consider a world that has certain locations and places that are of interest to the agent, and based upon what is true and false, or what values are associated with those locations, the agent could then make a decision, and that decision was based upon some sort of constraint satisfaction, solving some constraint satisfaction problem. Things like simulated reality, using swarm technology. So this is around the time when it was very much, it was very interesting for companies like Sony, who wanted to have huge, large crowds of agents running around complex environments and doing sensible things. And this was something that was very difficult to solve. Cellular automata is a kind of program where you divide the world up into these cells. They could be cubes, they could be hexagons. And based upon an algorithm that looks at that cell and what is the condition of neighbouring cells, say some sort of environmental conditioning, decisions could be made about updating a given cell. And basically a cell automata goes through each cell and looks at that cell and its neighbourhood and then makes a decision about an update of that cell. So you could have agents, you could have many agents in a cell or autonoma, or you could have an environment that had interesting effects. For example, clouds now are done with cellular automata. You could have worlds where you had land masses that were moving in a way just based upon rules using cellular automata. You could have agents that were moving in the environment because they themselves were the object of the cellular automata as well. Pathfinding pretty much became very important in the 1990s, particularly when you had agents that had to run around in 3D environments. This is around the time when Wolfenstein came out, around the time when the first versions of Doom came out. There's another game like Hexen, which is really just a rip-off of Doom. And so having agents in 3D worlds that could follow pathways was very important. And also things like smart environments. So towards the end of the 1990s, we saw things like The Sims. And The Sims what makes The Sims very interesting is that rather than putting all of the code into the agents, rather than putting all of the code into these characters that you're moving around, the code that tells the agent what to do was embedded into the objects. So in The Sims, when your character comes up to a fridge, for example, the character actually, non-player character, or your character actually knows nothing about how that fridge operates. But in order for the character to perform the right animations and to do the right things to interact with that fridge, the fridge had within it all of the code needed to tell that agent what to do. And the nice thing about that, it meant that in The Sims, you could write, you could create a fridge and encapsulate that fridge with all the code that was needed for the agents to interact with it outside of the software itself. So once The Sims had been released, people could create mods of objects and upload them into The Sims. So basically, a character would come up to a fridge, the fridge would tell the character how to animate when interacting with the fridge, and then suddenly the character would do all of the right actions, opening the door, pulling something out of the fridge, making some sort of happy noise or something when they found the right thing, or a sad noise when they found something that was rotten in the fridge. Really the 90s was a great explosion for a lot of different methods in AI for games. In the 2000s, now this became interesting, but I don't think that it was a huge success. But in 2000, there was a lot of ideas around using planners, artificial planners for video games. So the very first game to do this was actually Fear. That was actually one of their sales pitches was, oh, we're using a planner in our game engine, and our agents are actually able to plan what they do. And if you've ever played Fear, you'll find that a little bit too much of the resourcing was put into this planning, and not enough was put into some simple kind of AI, for example, detection of the player, proximity to an agent, and so on, or just some simple pathfinding. So what would happen in Fear is that you could run through the environment, and in some place, I mean, it was actually quite difficult. You could really lose in that game easily. But in some places you could walk into a room and there'd be agents standing there. They wouldn't know that you were there because they were too busy computing their planning algorithms. And you could just walk straight up to an NPC and shoot it. Or you could stand behind something and start shooting it before it realised that, that it was under attack and had to change its strategy. So it didn't implement it very well, but at least they started to implement planning. One nice feature about it was that sometimes you'd run through the environment, and you would, so you have that cognition where you memorise different rooms and different places that you've been in a game. So you'd run through the game and you'd go through a doorway. You'd be in this room, you know what that room looks like. You go through another doorway and you remember that you left that door open, you left that last door open, and you've come down some other hallway and down some stairs. But there's been another agent that you didn't see in the background who's also gone through that room and has then done something like close the door, moved a table in front of a door or something like that. And then all of a sudden you find yourself under attack. You think to yourself, oh, I'll go back through those same two doors that I just went through. And you go back, but you can't because another agent has already done some planning and has changed the landscape of the environment by closing doors and moving a table. So that was interesting in that respect, but at the time, computers really didn't have the resources to do it. Yep.
If you consider that a planner, what would you consider like the AI in something like StarCraft or other strategy games?
So when you're talking about strategy games, I think it relates more to AI for board games than it does for... you can have... So I wouldn't say in strategy games they necessarily do a full search of the space like you do in a board game, but they might do a local tactical search in order to come up with some sort of local tactic in order to win. So strategy games are very closely related to board games, but there's a different dynamic that where you can't actually apply a full search like you can in a board game. But they also use other things like pathfinding for doing, the low-level things like moving from one location to another. Yeah, yeah. Okay, so with respect to the game industry, what does it mean to implement artificial intelligence? Well, what it has meant traditionally is that it occurs towards the end of the game development. And there's some fairly fundamental reasons for this. A lot of video games, particularly around the 90s and the noughties, were very much focused on high-resolution graphics, having really slick rendering, having agents that had really good, could express really good facial expressions, could have realistic sort of human movements and that sort of thing. So a great deal of effort and resources was put into video games in order to exhibit these kinds of properties. So it has meant that AI has always been at the end of the build chain. It means that AI becomes, it becomes something that can be sacrificed for, better visual effect. It means that there's always been limited resources available to game AI. It means that the software that you write for artificial intelligence really has to be lean and fast. Fortunately, with a lot of game engines now, a fair bit of AI that you want to use is already pre-built into the engine. So that means that all of the really optimal code for that has already been written. But if you want to write new artificial agent methods into a game engine, you have to get right down to the level of C++. You have to really optimize that code. You have to look at ways to use memory effectively, to use CPU resources effectively, and to come up and to apply algorithms that are really optimal and efficient in their approach. There's also this thing, sometimes quick and dirty solutions are used. For example, a nice sunset scene to distract the player from some, not very good or unconvincing AI effect is often used. So there is this fact about video games, is that we have users who are very visually excited about the game, and anything that you use that is visual and it's sensational can distract a player from a lot of bad effects in a game. As stated here, because a lot more is being exported onto the graphics card and also onto physics cards and so on, there's more resources being made available to AI. So game AI is always emerging. So every year I say this, it's emerging, it's always emerging. We'll always have more resources, and as there's more resources, we'll be able to apply better methodologies and approaches to artificial intelligence, and our agents will be able to do more and more interesting things as we get much more power under the hood. All right, so there has been industry-funded research. For example, the University of Alberta had a games group for a while there. I'm not sure how good that link is. I think they still have the website there, but I think now the information there is getting a little bit old. I don't think they've made the kind of impact that they wanted to make into the game industry when it was big. But they certainly did contribute quite a bit in terms of AI research into industry applications. The other aspect here is that the industry has explored AI and the methodologies and approaches without any formal constraints. So what it means is that they'll just go and do something, and sometimes without really knowing the full limits to a problem or the difficulty of a problem, they could come up with a solution that was interesting and was very useful in video games. But the problem with this, from a research standpoint, is that there's been a lack of rigour in their methodology. So if we think about the application of planning in the FEAR game, in FEAR, the implementation, so the research required to implement that properly was never done. You know, there was nothing that one could really learn from that. The methodology wasn't really, you know, well considered. It wasn't really well documented. So from a research standpoint, not much could be said about that application, although from an industry standpoint, it meant that they could sell games, and a lot of players were very interested in playing it because of these new technologies being applied. Right, so game AI in academia. Now, this is where it falls short on academia. The transition here, like, there's been a transition that's taken place, but it's been very slow coming. So artificial intelligence is an aspect or an area in computer science, but it very much deals with more formal methods. And here, there is no constraint on how fast an algorithm operates. A solution in artificial intelligence in general could run on a computer for months before a solution is provided, and that is perfectly valid in academia. We then write up papers about what we found and so on. The problem is that that can't be applied in video games, because video games require approaches that respond quickly, you know, within milliseconds, within seconds at worst. So the transition has been difficult because methods that are seen as very important in academia can't be necessarily applied in computer video games, and methods that can be applied in computer video games aren't seen as being very important in academia. So the challenge is to precipitate a formal context for game AI that supports formal game AI studies. So that is, in order to get game AI into academia, we have to do this in a formal way, and we also have to change the context. What is important here? Is it that we have methods that are able to solve very difficult problems, or is it that we have methods that are able to solve problems in very small spaces or amounts of time? And I think that challenge in itself makes it worthy of an academic study, that we have very small amounts of time in order to solve a problem that, you know, is quite difficult, and the solutions to those problems have to be very innovative. Then there's also this aspect, what's called serious games and simulation tools. So there are whole industries out there that are very interested in 3D simulation. So just take, for example, mining. A lot of mining training is very dangerous. So when they train miners, they actually take them down into mine shafts. They actually put them through training scenarios, which are actually dangerous. The other side of that is that they use huge amounts of money and resources to do this training. And what the mining industry have realised now is that, we can use 3D simulation tools. For example, down in Newcastle, they have a mining training centre down there. They have this huge tank, which is an immersive 3D environment. And when you stand in this tank and they switch on the simulator, it's as though you're standing inside a mine shaft. And all around you on this tank, on the wall, you have this projection of a 3D world, basically, and you're completely immersed in the environment. So serious games and simulation tools are massive. It's not just for flight simulation, it's for mining, it's for all kinds of process work. Industrial process work would like simulators. Town planning likes simulators now. So there's a whole heap of work out there dealing with serious games and simulation tools that are not related explicitly to the game industry. All right, so what I'm going to do now is I'm going to show a dichotomy between traditional AI methods, the AI methods as you would have been taught in the past through different units in artificial intelligence and academia, and then game AI, which is the AI that's actually being applied in video games. So this is just a sort of example. It gives you a kind of idea of the kind of thinking that you might have to apply. So we consider this problem. We've got this NPC monster. This has got this guy here. He cannot see the player, and that's the player here, but needs to predict the player's location. So in traditional AI, so in the academic perspective, there's a number of ways that we might model the problem. But one way might be that we would model the problem as a dynamic Bayesian network, for example. And from that, you would determine the probability distribution of the player's location, and then you choose location with some high expectation. Why does academia do it this way? Because it relates to a whole host of other problems. You might have a robot that's out in the real world, and it needs to, based upon some information that's already seen about the world, try to predict where it is in the world and what the map looks like. So this is what's called simultaneous location and map SLAM, and that's a Bayesian approach. And so it's interesting from an academic perspective because it's doing all the right steps. It's it's proposing a model for the problem. It's then using the formal methods of that model in order to predict a probability distribution or determine a probability distribution, then using that distribution to make a prediction of where the player is. So it makes it interesting for a very wide class of problems. You could write a paper on it. It'd probably be accepted in a journal or a conference somewhere because of its wide-scale application. However, it's not very good for video games because it's going to take a lot of processing time. It's going to take a long time for the processor to come back with an answer. What we need in video games is that we need the solution to return very quickly. It needs to be within fractions of a second, milliseconds. So in video games, because everything is sitting in software, the solution is really simple. We just index the player's memory location. We get the player's position as a set of coordinates in space, and then we choose an arbitrary point in the neighbour of the player. And this can be computed very quickly and has exactly the same effect. Very fast solution, but it has limited applications outside of computer games. There's nothing about this that's interesting from a research standpoint. It's simply a lookup and finding a random point next to another point. And that's the challenge. We need to make this academic, we need to find a reason why this is important from an academic perspective. All right, so we have two worlds, and this unit is straddled somewhere between these two worlds. One of the worlds deals with traditional AI, so it's dealing with the academic perspective of it, and the other side is dealing with game AI as it's applied in video games for the purpose of creating a visual and artificial agent effect. So we'll be taking a little bit from column A and a little bit from column B, so that it has an academic import and also has an industry import into the game industry. All right, so there is some stuff that's fairly useful from column A when we're dealing with agents. It provides a formal way or a formally constructed way to talk about agents and what they're actually about, what their components are about, which is vastly different from the industry, which will talk about agents in terms of software and classes and methods and so on. So from column A, we can talk about agents having different components. So an agent has something that's called a sensor, and a sensor is any system that can measure some parameters of the environment. Okay? So if you think about a robot might have some cameras and it might have some pressure sensors on the side of the robot. So if it runs into a wall, the pressure sensor is activated and knows from that signal that it's run into a wall. Or the camera could be used to make some sort of decision about the landscape, about whether there is a throughway or not, and it might use that in order to build up a map. Well, the same thing happens for artificial agents in a video game, except our sensors in a video game are not cameras or pressure sensors. They are things like events that are occurring from other areas in the software. So if you think about a 3D environment, an event might be that certain doors have been opened, or another event might be where the player is located in that environment, or where other NPC are located, or if something got blown up like a wall, that might be an event that the agent wants to know about. And so those events become the sensor input to our agent. The other aspect of an agent are what's called actuators. So an actuator is any system that facilitates action. So if we think about a robot, again, a robot might have wheels or it might have legs, and so those are the actuators for moving. For our agent, however, in a video game, our actuators could be any kind of action that agent can perform. It might be things like running, jumping, swimming. Our agent might be able to climb up walls. It might be able to blow up. There's all sorts of things that the agent might do as an actuator. All right, so given these, an agent is anything that can perceive the environment through sensors and act upon the environment through actuators. So this is important in terms of fundamental features of an agent. Okay, so I'm going to introduce some concepts here. So this is the basic diagram that we'll be looking at for agents. We have this box here, that's our agent. We have our environment. We have our sensors, and our sensors receive what are called percepts. Something happens in this box, and that box is the AI that we're going to be implementing and looking at over the next couple of weeks. So whatever gets computed here ends up affecting some actuators, and then ends up mapping some actions onto the environment. So what then makes the agent what we call rational? When we look at an agent in a video game and we see the agent doing something that we think is sensible, we think some sort of intelligence is going on with those actions, we say, oh, this agent is rational. This agent is doing something rational in our perspective. If you're playing, for example, an artificial chess game, you notice that the agent is making a move, and it's a very clever move, and you think, if only I'd thought of that move, I would have won the game. What is it that makes this agent rational? Okay, so the key feature of that is what's called a performance function. And this will be a terminology that becomes important over the next couple of weeks. We'll sometimes talk about performance function. We'll also use words like utility function, objective function. But basically, it's a function that measures how well the agent is performing in doing something that is rational. So you'll notice I'm using these words, but their meaning is it's not real, okay? So the meaning of such things as rational is only with respect to a performance function. So given a performance function, an agent is rational if according to this function it performs optimally. So whatever your performance function is, that's what defines your agent as being rational. So an agent that follows a pathway, that's able to follow the pathway optimally, so it's able to find the shortest path, you might then deem the agent rational because it was able to do that. In other instances, that might not actually be your performance function. You might just want the agent to actually find a path, but you don't care if it's the shortest one. Then we have this idea, what is intelligence? You know, what makes the agent intelligent? And, well, you know, we can sort of load words on top of words here, and we end up saying things like a rational agent is an intelligent agent. So, in some respect, I'm kind of dispelling a myth here. You will have had this idea that, you know, agents might actually be intelligent. But the problem really is, from a philosophical standpoint, we don't actually know what intelligence is, have no definition for it. Turing, for example, had what was called the Turing test. And the idea was, if we put a human being inside a room and we put our computer inside another room, and we weren't told which room had the computer and the human, but we were able to ask a series of questions. If we couldn't determine the difference between the responses from the computer and the human being, given sufficient number of questions, then Turing proposed that the computer was intelligent as a human, and therefore exhibited the property of artificial intelligence. That's probably not a bad way to define it. You have a human being as your template or your model for intelligence. But still, it doesn't actually define what intelligence is. When you then look at the program of the computer, what procedures was the intelligent? What functions being executed was the intelligence? So really, because we don't have a definition for intelligence, it doesn't exist in terms of computers and agents. It's a word that we use because when we look at the agent, we're tricked into believing that it's doing something intelligent. And really, I guess, part of the problem is as human beings, we're very easily fooled. And that's really what artificial intelligence is. It's about doing something that very easily fools the user into believing that agent is intelligent. And so, at the fundamental of it all, intelligence is really just the end result of a performance function. And so that's really the context that we're working in here. We're really dealing with mathematical concepts. We're really dealing with functions. We're dealing with measurements, because that's how we write software. We've always written software this way. We've always based our software upon processes and measurements and calculations. We have no other way to do this. So it leaves us in this limited place. The problem of measuring performance can be simplified if the agent has a set of goals, for example. So a lot of our agents are goal-based. Pathfinding, for example, is goal-based. We set a location somewhere, that's the goal for the agent. The agent then has to find a pathway to that goal. And because we have a goal, we can then set a performance function because we might consider the shortest distance or the shortest pathway to that goal as our measure of performance. So a goal is a state of the world where the agent was successful, and performance could be anything. It could be a measure of distance, it could be the probability of the agent achieving one of its goals for a given world state, and so on. All right, so I'm going to give a little example here. This relates to a board game, and this is a really miniature version of that same board game. Usually the board has 11 rows this way and 11 columns this way, but here I'm just using a 2 by 2. And the objective here is that black has its opposite sides and white has opposite sides. And the white player has a cache of stones, the black player also has a cache of stones, and each player places a single stone on the board in an empty cell, and each player places a stone alternative to the other player. So one player has a turn, the next player has a turn, and so on. Now, I've done it like this because it's really simple to show on a very small board. But basically, the first player to play will be black, and so we consider all of the different positions where black has placed the stone. And then we consider all of the different positions after that where white has placed the stone, and so on. Now, if we care about white winning, what white has to do is create an unbroken chain of stones between her two sides. So the goal state for white are all of these board positions where she has an unbroken chain between her two sides. Now, for her to play rationally, to be an intelligent agent, she has to search this whole space, and given all of those positions where she wins at a goal state, deduce which move that she has to make all the way up here in order to arrive at that winning position. So often our agent is looking at a space like this. This is what is called a state space. It's a space of all possible states for our agent. And an action in this state space is given by a transition from one position to another. So this is the initial state, for example, and then the white player, she makes a move, and that move is an action that changes the state, that creates a transition from one state to the next, or from one state to its successor state. So this idea is important. We have a state space full of states, and an action is could be represented as a tuple of two states: the state that the world was in before and the state that the world is in afterwards. Okay, so how are we going for time? Oh, okay, I was going to give you like a 5-minute break, 10-minute break. So let's do that, and then I'll go on to the rest of the lecture. Okay, just let you know the recording's begun. Okay, so we were just talking about rational agents and perhaps even some philosophy behind that. Now, in the diagram I showed you earlier, there was this agent diagram, and there's this box with this question mark. Now, we need to start talking about what that is. What this really is, it's a mapping function. It's a function that maps a set of sensor inputs into a set of actions. So in some respects, your sensor input is kind of a representation of state. Well, it is a representation of state, but it's not a complete representation of state in all cases. And what we're after here is a function that maps this representation of state to a set of actions that we can apply to our actuators. And this function is something called a policy. So a policy is a function that maps states to actions. And often when we're dealing with performance functions, we are then also talking about what's called an optimal policy. And, well, an optimal policy is one that performs optimally. Notice the truism there. I mean, it's fairly, well, useless statement. But it is really the case. We're often considering a performance function, and so we want a policy that performs optimally according to that function. And then the argument goes this way: an agent with an optimal policy is rational, and rational agents are intelligent agents, and blah, blah, blah. So that just ends up becoming the chain of rhetoric that goes, or philosophical rhetoric that goes towards arguing what is intelligence and so on in terms of computer science. All right, now from column B, now from the game industry perspective, we have a lot of parallels, but they use somewhat different terminology. An avatar is an in-world character representation of a user, so this is not a non-player character, this is a user. Computer games have two types of characters. They have the player and they have the non-player character. excuse me. And the player character is an avatar that's under human control, and a non-player character is any agent in the game that is not under human control. Players and NPCs interact through software architecture of the game, and this architecture generally has the following features. It has game state. Now, game state is very much, it's really about state space. So when I was talking about state space before, and we had states within that state space, game state is really just some data or some memory allocated and some software around that memory allocation that represents the state of the world at a given point in time. So it's just simply the current state of the world. That might quite literally be everything that's being rendered in a 3D environment, for example. Then we have another software package or software engine, if you like, called the simulator. And that's a system that applies a set of state transition rules along with a set of related animations. So when I say state transition rules, it's not as simple as some rules as in a lookup table, but it's some software that makes some sort of calculation or some whether it be statistical, whether it be state-based, whether it be search-based, but it makes some sort of decisions that ends up affecting a transition of state. And that transition of state is really a transition of the game state from one game state to the next. And that is then done through a set of animations that you see within the game state, particularly if it's a 3D environment. Then we have the renderer, which all things associated with 3D and 2D rendering of the game state is then ported to the screen or to whatever device that you're using to look at the game. And finally, we have controllers, which is the input that the users are applying in order to put input into the game. Now, this is also related to the non-player characters as well. So the non-player characters can also have or induce control into the environment. So generally the architecture looks something like this. We have, starting with game state, we have this being updated by the simulator because the simulator is generating transitions of game state. So the simulator receives the current game state, does some computation and returns an update to the game state. This then gets ported down to the renderer, and so you see the game changing over time based upon things that are happening in the game. There's also the controllers, which are the actions that the player is providing into the game environment by moving their player around, their player avatar around. And there can also be actions that result because of what the NPC are doing. They might also have some input to the controls. So information comes from the game state that tells the controller in some instances where and how the player can move. These actions get fed to the simulator, and the simulator then processes those in different ways. So, for example, you might have a character that you might have a non-player. You might have your player as a character that has just moved forward into some water, and what the simulator then does, it has to then maybe put your character into a swimming mode, and so suddenly your character is now swimming. And that has to then be updated with the game state and then rendered to the output. Right, in game engines, such things as the renderer and much of the simulator physics engine are built in. The features most interesting for us, and this is important when we deal with Unity 3T because this is exactly what we'll see there. The features most interesting to us is the game state representation and somewhat the simulation, so things like pathfinding, avoidance, and the controllers, so high-level decision making. So we begin with game state as this is our input of the agent. So our agent actually needs to know what the game state is in order to make a decision about what it will do next. So it's very much a software perspective. So game state could be given as a runtime record. We're dealing with software after all, containing every in-world feature that is important to play. So we might have things like the velocity of the ith character could be a feature of the game state. And the game state might be represented by something like a class. And you can then query it for things like what is the velocity of character I, and then we would get a vector back with a certain magnitude and direction. And it would look something like this. You'd have a class and you'd have different methods. I mean, I'm really just showing a class diagram, a class skeleton here for a game state. But it's something like this. You'd have things like being able to get the number of objects, being able to get a certain object in the environment, getting the number of characters, being able to access that character, and then being able to query objects and characters on different properties that they have. All right, so this is very similar to what you'll see in Unity 3D. As you discover more about Unity 3D, you'll find that the features that I just talked about do indeed exist. So we can check out the referencing script, go back. All right. So if I take this link, for example, I just want to go. All right, so this is the API for Unity 3D, and you see things like the Unity engine has a whole heap of functions on here for scripting, for rendering, for audio, for example. What else have we got here? Scene management, networking as well, and there's classes here for doing animations. There should be one here for behaviour. Might be under something else. What? I missed it, did I? Yeah. Oh, here we go, for behaviours. And this mono behaviour, for example, is a set of behaviours that you can attribute to objects and also to characters as well. So you find that you have all of these classes, and these classes then have all kinds of methods that you can associate with objects. So things like find an object of type. What else? Maybe under mono behaviour might get a better list. On animation, do something. On animator, move. On collision, so you'll have collision meshes associated with objects, which will be accessed through mono behaviour. Different events that can be executed based upon things like collisions. Whether you click the mouse on that object. So there's a whole host of functions that suddenly become available because you have objects in the environment and you have certain classes associated with it. So as you can see here, the Unity 3D environment is identical to what I was just talking about. Well worth looking at that reference also. Okay, so before next week, so I'll just wrap up this lecture today. So before next week, there are some things that you need to do. Access Unity 3D, so get a version of Unity 3D on your personal computer. Or alternatively, actually it shouldn't be alternatively, or access Unity 3D in the computers in the Game Lab, S515, or both. Get them on your computer and access it in the Game Lab. Read the user manual. As I pointed out, this user manual is very good, and also is associated with a number of tutorials, which will also help you get familiar with Unity 3D. Now, next week in the workshop, we will create some simple objects in Unity 3D and just do some simple scripting exercises. So as I pointed out, for many of you who are familiar with Unity 3D, this will be sort of fairly, big pardon? This will be sort of fairly simple, but for those who haven't had any experience with Unity 3D, this will be essential for them to get up to speed and able to use it. So it won't detract from what we'll cover very quickly in the next couple of weeks, but it is important that I get everyone up to the same speed and using Unity 3D as we go forward. In World Assets, Unity 3D allows you to import 3D third-party assets from their store. So they have a store, and the store sometimes has free stuff there. Well, it has quite a bit of free stuff, and also has paid stuff. So it's easy to access that and to import assets from their store that's free. I don't expect you to buy stuff, and you should be able to do assignment work for this unit without having to purchase anything from their store. So another point there, Unity 3D needs to actually be online to access the store, and you'll need to create an account as well. All right, so next week in terms of content, we'll look at some discrete structures, and this will be important for looking at navigation and searching. We'll look at some structures called graphs and trees. So graphs are not what you might have been taught in terms of a plot for plotting mathematical functions or anything like that. A graph is a structure that contains nodes and edges, and sometimes those structures can be sometimes those structures can also form trees. We'll look at what's called weighted graphs, that is where we have a weight on the edges, and those weights are important for searching. And then we'll look at three main spatial representations. We'll look at waypoint graphs. We'll look at navigation meshes, which is a very common way for calculating pathways in video games. And we'll look at a kind of navigation called a grid, which is also a very efficient way to represent space and for doing pathfinding. Then we'll look at the problem of pathfinding, and we'll look at such things as heuristic functions, and then we'll begin with a very simple kind of algorithm called the greedy search algorithm, and why that might be useful for video games. Okay, so that wraps it up for this week. I'll catch you all next week. If you have any questions, just come and see me. I'll be here for the next couple of minutes.